All right. So this is section 7.4, part 2 of part 2. And this is when we are actually starting to change the amplitude of our functions. So these first two pictures up here, and these are the only ones that you'll see, again, are the linear change or the exponential change. And so here, this one, you can see this is an exponential change. And with amplitude, you know how amplitude is reflexive because, you know, that the high and the low is always going to be the same. So the amplitude then looks like it is reflected across that x-axis. And then the amplitude just runs in between those two equations all the way down. Okay, so that's what happens when our amplitude is changed. And now this one over here is a linear change. So this is going to be the equation that we define as changing the amplitude, and then it's reflected across your x-axis. And then that shows exactly where your amplitude is going to run between. So it's going to be enclosed within those two lines. Okay, so we call this damped harmonic motion. And damped harmonic motion is exhibited by springs subject to friction following a model of these two formats. So f of t is equal to ab to the t sine of bt plus k. And these can also be cosine. They're just identifying each of them, showing you how they're set up with a sine function, but they can also be cosine. And then this one here shows your amplitude is a linear change. So this one here is going to be linear, and this one here is going to be exponential. Okay, so for example number 4, this is our first example with a spring. And so we have a spring is attached to the ceiling and pulled 16 centimeters down from equilibrium and released. After 2 seconds, the amplitude was decreased to 5 centimeters. The spring oscillates 13 times each second. Assume that the amplitude is decreasing exponentially. Find an equation for the distance d. The end of the spring is below equilibrium in terms of seconds t. All right, this can be a little bit overwhelming when you first read all of this whole story problem, but let's break it down little by little and we will go from there. First thing I'm going to pick out of this equation here is that it says assume that the amplitude is decreasing exponentially. So what that tells me right off is that I am going to have an equation that is in the format of y equals ab to the t power. Okay, and so that we will be able to figure out right away. So that's going to be our amplitude. And they give us some information here. I'll tell you how. We'll figure that out here in just a minute. Another thing that we can easily pick out right here is it says the spring oscillates 13 times each second. Well, I want you to recognize that as frequency. So notice they are not giving us a period or how long it takes to get through one complete rotation. In other words, they give us, in this case, they give us the spring oscillates 13 times in each second. So that is a frequency instead of a period. So that is going to be the frequency f. However, if we know f, we can very easily find p. So if f is 13, then p is 1 over 13. Now, b is what we need to find our equation. So b is 2 pi over p. So far, that's what we know. But if we wanted to write p in terms of f, we could also say b is 2 pi over 1 over f, right? Because p is the inverse of f, which then we could say that b is equal to 2 pi times f. So if they ever give us a frequency in an equation, we can do 2 pi times that frequency. you can always just go in and find your period and then go back to your b equals 2 pi over p. That works every time also. But if you want a little bit of a quicker route, if you can remember it, not get confused with all of these different things, then you can remember that b equals 2 pi times f. So in this case, they are giving us f, the frequency is 13, so b is going to equal 26 pi. All right, so we're starting to figure out things little by little. So let's keep going through this. This says a spring is attached to the ceiling and pulled 16 centimeters down from equilibrium and released. So at the very beginning, at time 0, right, this is right when we're starting, so at time t equals 0, our spring is pulled down. So now let's kind of draw a little bit of a picture. We've got a ceiling and we've got a spring on this ceiling. All right. And then we're going to pull this spring down. And it's being pulled down 16 centimeters from equilibrium. So this right here, distance, is 16 centimeters. So if we are measuring this distance d, this is going to be the longest that this distance is going to be. So when we think about the graph of this equation, our midline is our equilibrium. Okay, so make sure you realize here this is our midline. This is our equilibrium. That's my x-axis in this case. But 16 is not a negative number. That's positive 16. So when we're pulling a spring down from the ceiling, we want to think of that kind of as an upside down equation. It's when you look, I think of the graph of it, it's going to be opposite of what you think. Okay, so think of that as being up here. If you can remember that, you'll know that this is a cosine function because it's starting at its longest distance, you could say, from the ceiling. And so other thing you can do is always just throw in a cosine when you're doing a spring problem. You'll most likely have it correct. So spring problem, cosine. Just remember that. Okay, I think we're ready to at least throw in a shell of what our equation is going to look like. So we have the amplitude, which is exponential equation. I'll show you how to find that in a minute. And it's going to be cosine. We found our b value up here. Our b value is 26 pi. Don't forget your variable. So 26 pi t. And then because we're going to put that midline at the equilibrium, we are not moving up or down any. Okay, so midline just stays at 0. So there we go. That's most of our equation. Now what we have to do is we have to figure out what a and b are. Let me give myself a little bit more room here. And we are going to get rid of all this. And now we're going to use this side over here to solve our equation. So our amplitude is going to be in the form of a times b to the t. Now they give us all of this information. This whole first 2 sentences are dedicated just to our amplitude. So it says that it is pulled 16 centimeters from equilibrium at time t equals 0. We can write that as an actual coordinate point. At time t equals 0, the length of that spring is 16 centimeters from equilibrium. That actually gives us a point on our exponential line right here. Okay, they also give us another one. Then it says after 2 seconds, the amplitude has decreased to 5 centimeters. So t is in terms of time, and that's our x value. So this one is 2 seconds and 5 centimeters. So they've given us 2 points. So if you can always pull out that information, write 2 points, then we can plug those points into this equation here and work our equation from there. So first let's work with the 0, 16. So what happens when we plug in 0, 16 to this equation? I'm going to show you the whole thing. Some of you might be able to think ahead far enough here to know what I'm getting at, but I'll show you all. So we get 16 equals a times b to the t, which is 0. So b to the 0, what happens when we raise anything to the 0 power? We get 1. So now we end up with 16 equals a times 1, which is just a. So now, as far as the equation goes, we know we have a equals 16 b to the t. Now if you can think back to when you worked on exponential equations before, those exponential equations, a lot of times we would write them as a naught or a sub 0. And remember that that always represented an initial value. So that a is always an initial value. And they will always give you an initial value on these spring problems. And that initial value looks like this. When the spring is attached to the ceiling, pulled 16 centimeters down from equilibrium, and released. So when it is released, that's when time starts. It's 16 centimeters down from equilibrium. So 16 is always that initial value, and well, whatever value they give you there, it's going to be different for each question. But for mine, it's 16, and I can take that first value, the initial value, and plug it right in for A. Okay, then they give us a second point. So let's come down here, bring our point, the 0.25, and then remember that first value is always t, and then this 5 is our y. So we have 5 is equal to 16b squared. Now we're going to divide. We need to solve for b. That's our last thing that we're looking for. And maybe that's a good thing to note somewhere too, that when you are solving this equation, to get an equation that we can put in, we need to solve for a and b. We need to find what a and b is. Then we can write that equation in. So we have 5/16 is equal to b squared. Solve for b, we'll take the square root of both sides, and we get b equals 5 over the square root of square root of 5 over the square root of 16, which is 4. So b equals the square root of 5 over 4. Now let's go ahead and write that exponential equation. I think we've got everything that we need. So we have y equals a, which we said was 16, times the square root of 5 over 4 to the t. All right, now be very careful here. If you do not put parentheses on here, to the t power, either way, whatever you do, whether you have parentheses on there or not, don't be tempted to cancel out the 16 and that 4. All right, because that 4 is being raised to the t power, the 16 is not. So those are separate. So we can't cancel anything that's in there. And then when you put it into My Open Math, you're going to need to make sure and put all those parentheses around there so that it knows you are raising both of those to that power of t. So we're ready to write our complete answer. So we have d of t is equal to a, which is 16, times b, which was the square root of 5 over 4, in parentheses, to the t power. Ooh, I'm almost out of time too. And cosine of 26 pi times t. All right, and that's your answer. So hopefully you can kind of wade through that and make sense of it. I don't think it's too hard once you really get into it and understand what each one of these pieces is giving you. But yeah, it might take a couple of times going through some examples to really understand that. And let me know if you guys have any questions. Go ahead and send me an email or a text.